Drop a stone and it falls fast. Drop that same stone into a jar of honey and it drifts down in slow motion. The difference is drag, the resistive force a fluid exerts on anything moving through it. And remarkably, that force follows two completely different rules depending on how fast the object moves. When any solid object moves through a fluid, a liquid, or a gas, the fluid pushes back. This resistive force is called the drag force, and it always opposes the object's motion. It is one of the most complicated forces in mechanics because it depends on the properties of both the object and the fluid it moves through. Two sets of properties control the drag. On the object side, its speed, its size, and its shape. On the fluid side, its density, its viscosity, and its compressibility. Change any one of these and the force changes. Because so many factors interact, there is no single simple formula. The force is genuinely hard to pin down in full. The key to taming this complexity is speed. For a rapidly moving object, like a ball thrown through the air, the drag grows with the square of the speed. For a very slowly moving object, like a grain of sand settling through water, the drag grows only in direct proportion to the speed. Fast and slow obey different mathematics, so we treat them separately. Start with the fast case, objects moving rapidly through air. Experiment shows the resistive force is roughly proportional to three things: the square of the speed, the cross-sectional area the object presents to the flow, and the density of the air. Notably, at these speeds, the drag does not depend on the air's viscosity at all. Viscosity simply does not matter when things move fast. We can gather those proportionalities into a single equation. The magnitude of the high-speed drag force equals 1/2 times a drag coefficient, C sub d, times the cross-sectional area A, times the fluid density Rho, times the speed v squared. The 1/2 and the drag coefficient absorb all the messy details of shape and flow. Everything else, area, density, and the speed squared, is exactly what our intuition predicted. That drag coefficient, C sub d, deserves a closer look. It is a pure number, dimensionless, that captures how streamlined or blunt an object is. A sleek shape slips through the air with a small coefficient. A blunt shape drags a large one. Each value in the table that follows was measured at a Reynolds number of about 10,000, a standard benchmark for this kind of flow. Here are drag coefficients for some simple shapes. A sphere comes in at about 0.47. A cube, blunt and flat-faced, is much higher, at about 1.05, more than double the sphere. Turn that cube edge on and it falls to 0.8, but look at the streamlined body, just 0.04, more than 20 times slicker than the cube. Shape alone can change the drag by more than a factor of 20. This quadratic law works for air, but it does not carry over to every fluid. Drop an object into oil, molasses, honey, or water, and each one falls at a different rate because each has a different viscosity. To describe slow motion through thick fluids, we need an entirely different law, one where viscosity takes center stage. In the slow regime, the physics simplifies in a different way. At very low speeds, the drag force is directly proportional to the speed. Double the speed, double the force, and it is also proportional to the fluid's viscosity. Thicker fluid, more drag. This is the reverse of the fast case. Here, viscosity is everything, and the speed enters only to the first power. For one special shape, a sphere of radius r, fluid mechanics gives the slow speed drag exactly. The drag force equals -6 times pi times the viscosity eta times the radius r times the velocity v. This is Stokes' law. The negative sign means the force points opposite to the velocity, always resisting motion. And notice the structure. The force rises in direct proportion to the radius, to the viscosity, and to the speed. No squares anywhere. This viscosity, eta, has a concrete physical meaning. It measures a fluid's internal resistance to flowing, its thickness or stickiness. In SI units, viscosity is measured in Pascal seconds, which is the same as kilograms per meter per second. You will also meet an older unit called the poise. The larger the viscosity, the more sluggishly the fluid flows, and the harder it resists a moving object. These typical viscosities span an astonishing range. Air is extraordinarily thin, about 1.81 times 10 to the minus 5. Water at 20 degrees Celsius is roughly 1.002 times 10 to the minus 3, about 50 times thicker than air. Olive oil climbs to about 0.081, glycerol to 1.2, and corn syrup to about 1.4. From air to corn syrup, viscosity leaps upward by a factor of tens of thousands. The slow speed law governs the world of tiny things drifting through fluids. Picture very small water droplets falling through the air under gravity, grains of sand slowly settling to the bottom of a pond, or molecules sinking through a liquid, a process called sedimentation. In every case, the object moves slowly enough that Stokes' law sets the drag. Sedimentation hides a beautiful scaling argument. Model a molecule as a tiny sphere of radius r. Its mass grows with its volume, so the mass is proportional to r cubed, but its Stokes drag is proportional to r alone. Since acceleration equals force divided by mass, the drag per unit mass scales as r divided by r cubed, which collapses to 1 over r squared. So larger molecules feel relatively less drag per unit mass and settle differently from smaller ones. That size-dependent settling is exactly what laboratory machines exploit to separate molecules by their molecular weight. So a fluid's drag wears two faces. Move fast, and the force climbs with the square of your speed, tuned by a shape-dependent drag coefficient. Move slowly, and the force rises in step with your speed, tuned by the fluid's viscosity. Unlike the friction between two solid surfaces, which barely cares how fast you slide, fluid drag depends sharply on velocity. That single fact, force shaped by speed, is why swimming feels nothing like walking, why a frisbee flies, and why engineers labor over the shape of every aircraft. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.